Hello, welcome to another module of this course, Microwave Integrated Circuits. We are in the week 7, module 4. In the previous module, we had covered various aspects of noise, how noise originates, how to characterize noise, and then we also introduced the concept of noise figure and noise measure. And then I mentioned how to adjust or how to arrange stages in cascade so that you get the lowest noise figure overall. Now in this module, we will be covering the noise figure circles, or how to design a circuit which has a given requirement of noise figure. How do we design that circuit so as to achieve a particular value of noise figure? So in this module, we'll be proceeding just like in the same way that we proceeded for the gain circles. That is to design a circuit having a particular value of transducer gain, the unilateral case, or the operating power gain, or the available power gain. So let us see how to obtain these noise figure circles. So the first aspect is that we have our two-port network. This is our two-port network, and if we consider it to be a noiseless circuit, so this is our noiseless two-port network. And so what we have is two aspects or two quantities which have to be extracted. The input referred noise voltage and the input referred noise current. So this is port 1, this is port 2. Now suppose we have a noise source here. So it's a current source, now it can be shown that now suppose this is our entire arrangement. Okay, this is our input noise current source. This is the impedance or admittance of this noise source. This are the Vn square and In square of the input referred noise and noise voltage and noise current. Then it can be shown that the noise figure for a particular value of Ys is given by where we have this Y opt is equal to G opt plus J B opt. So what we have is 1, 2, 3. There are three quantities, this F mean, Rn and Y opt. If we know these three quantities, then we can completely characterize the noise associated, the noise figure associated with a two-port network. Now, GS here is given by this YS is given by GS plus JBS. So, it is the real part of YS. So, there is what this means is there is an optimum value of YS for which we obtain F min T F min. So, that is F YS equal to Y opt is equal to F min. This T is a argument just to emphasize that noise figure is a function of temperature. Now, this equation can be rewritten in terms of the normalized values like this. Now, here I am not writing the argument y, argument t. Where small y opt is equal to y opt on y0 Rn is equal to now this small y opt can also be written in terms of the reflection coefficient gamma opt like this. Now, and this ys is equal to ys upon y0 . Now, this noise figure F can be written as now it can be shown that for a constant noise figure for F is equal to constant, the locus of gamma s will be given as and then this Ri is given by this which when this Ni is given by this relationship, and we can show that this is like this. Now, if we plot these curves, these noise figure circles, these are the circles, this is the gamma s plane and we know that gamma S plane is related to the available power gain, because when we design a circuit using the available power gain circles, we are in the gamma S plane. And you can see that for gamma S equal to gamma opt, that is for Ys equal to Y opt, the radius of these circles is 0. For other values of gamma S, the radius, that is as the difference between gamma S and gamma Ys, and I beg your pardon, gamma S and gamma opt increases, the radius of these circles increases. So as I was saying that, this is the gamma S plane, and we can draw the available power gain circles. Now we know that the center of the available power gain circles lie on this line joining the origin with CA, and the radius for gamma S equal to gamma MS, that is the bilateral solution of the transducer gain. That at that point we get GA equal to GA max equal to GT max, and at that point the radius of these available power gain circles is 0. Now if we want to satisfy both the available power gain requirement and the noise figure requirement, then we choose a point where, suppose this is the available power gain circle we want to we have, and this is the noise figure circle for the desired noise figure. Then the point of intersection between the two will give the solution for both the noise figure and the available power gain. In the same way that we can draw noise figure circles, we can also draw noise measure circles, and I don't want to go too much into these noise measure circles, but they are useful sometimes. So if we come back to the slides, on the written slides, just like so noise measure of a stage is defined like this. So though not very common, but these for a constant noise measure not very useful, especially for single stages, but we can have noise measure circles where we trace the locus of gamma S for a constant m. If we just want to summarize this module, in this module we learned about the noise figure circles. We saw that there are 3 quantities which are needed to characterize, to write an equation for the noise figure of a stage, 2-port network. One is the Y opt, the F min, and the Rn. And we saw how we can draw these noise figure circles, and how we can, along with the available power gain circles, we can obtain optimum values of Ys to satisfy both the available power gain requirement and the noise figure requirement. Now this is a technique that is frequently used while designing low noise amplifiers. The derivations, though I have not shown for how we got that equation for noise figure, the derivations are given in the book by Gonzalez. I urge you to go through it once. Thank you.